Math 3 Lesson Summary Video, Sign Language. This lesson is a Solidify Understanding task, which takes concepts developed previously and helps you formalize those ideas. The purpose of this lesson is to use reference right triangles, triangle trigonometry, and the symmetry of a circle to find the y-coordinates on a circular path at given instances in time. An introduction to the circular trigonometric functions. Yesterday, Carlos figured out how high he could get on the Ferris wheel, but he has also noticed another characteristic. He has timed how long it takes for one carriage to get all the way around the Ferris wheel, and it takes 20 seconds to complete one revolution. This is what we call an angular speed. You may have heard of RPMs. Generally, we talk about RPMs as revolutions per minute. You hear this a lot when you talk about cars. It's how fast your tires spin. Revolutions per minute. So our Ferris wheel is revolving once every 20 seconds. If we want to turn it into an angular speed, we do want to know how many degrees we are revolving per second, or how many degrees. We could also say radians, depends on what you're measuring in, per time period. In this case, Carlos has figured it out in seconds. So if we do one full revolution, that would be a whole circle. So that would be 360 degrees. And we know that it does that one full revolution, 360 degrees, in 20 seconds. That means that our angular speed, if we reduce it, will be 18 degrees per second. So every second that you sit on the Ferris wheel, you're going to travel 18 degrees. Now that might not seem like much sense to you. 18 degrees, we're talking about this distance, the number of degrees that we have traveled from this center spoke. How far in degrees have we gone? When we talk about angular speeds, there's also a matching linear speed. Linear speed is something that we're used to. Linear speed is a distance over a time. Now, for us to find our linear speed, how fast are we traveling in the carriage along the outside rim of the Ferris wheel, that would require us to use some things from last unit's circle unit, the arc length. I would need to know how far in my arc length, or how far along the outside of this circumference of the circle have I traveled in a certain amount of time. And so we would have to find that arc length in order to find our linear speed. But our angular speed is talking about how many degrees have we spun in a certain amount of time. So if our Ferris wheel can complete a full rotation in 20 seconds, then it must be traveling at a speed of 18 degrees per second. Now that we know how many degrees per second we are traveling, if you remember yesterday, we figured out how high we were at different points on the Ferris wheel based on its inner angle. We could use that inner angle to help us figure out how far above 30 we had gone, or how far below 30 we were at the moment. And we used that angle at the inside here. What we actually call these triangles, when you're trying to find a point on the circle that you are spinning around the origin, around 0, 0, we generally call this a reference triangle. Every point on a circle around an origin in which we are spinning always has a reference triangle. And that is how we can find its location on the coordinate plane, on that circle around that origin. Today we're going to be using our reference triangles again because we still want to find the height we are on the Ferris wheel, but this time we want to know it in relationship to how long have we been sitting on the Ferris wheel. So we want to calculate the height of a rider at each of the following times, where t represents the number of seconds since the rider passed position A on the diagram. So we're counting our time passed here. So if we were loading onto the Ferris wheel at this point, we would be talking about the seconds that we are traveling counterclockwise around the Ferris wheel. Where would we be? So we're doing time versus height on the Ferris wheel. So for any given time, past point A, going this direction, we want to know our height. So if we are looking at these times, 1 second. So if I've only traveled for 1 second, we know that we are traveling 18 degrees per second. So this angle is going to be 18 degrees. And this is the height above 30 that we're looking for. And we learned yesterday that if we just do the radius of the circle, which was 25, times the sine of our angle, and our angle was 18 degrees, then we could figure out what that height was. If we look on our calculator, we can see that 25 times the sine of 18 is 7.7 feet. So after 1 second, we have traveled 7.7 feet up above the 30 mark. So our height is going to be 37.7 feet. Now, as we continue to go around, one of the things that we have to do is we're always going to have to figure out what is that reference angle to make our reference triangle, so that we can do our trig to actually figure out the height. This time we did 25 times the sine of 18. Now for 2 seconds, 18, so if we went 18 twice, that would be 36. Well, that was one of the triangles that we figured out yesterday. So if after 2 seconds, we know that we have gone 36 degrees, when we do 25 times the sine of 36, that was the one that we figured out yesterday, was 44.7 feet, because this turned out to be 14.7. Now we're going 2.5 seconds. So let's see, 18 times 2.5. So really, to figure out what our angle is here, all we're doing is taking our angular speed, the 18 degrees per second, and we're multiplying it by how many seconds we're going. So this time we would do 2.5 seconds. So that's how we're figuring out what our actual angle is that we're plugging inside of our sine. And so if we do 25 times the sine, of 18 times 2.5, so that's going to tell me how many degrees we've traveled in 2.5 seconds, we get that that height is 17.7. Now that is a height above 30. It's going to be somewhere up here, a little past this one. And so that's going to give us a 17.7. Add that to the 30, and we get 47.7. So everything seems to be going great. I think we've found a pretty solid pattern that we're following here. The radius always stays the same. We're always taking the sine. And then we just need to figure out how many degrees we've gone, because then we'll have our triangle if we do 18 times our number of seconds. So 18 times 3 gives us 54 degrees when we plug that in. And I'm sure we'll get a perfectly fine answer. But I'm looking down here at 8. And 8 seems a little weird to me, because if I do 25 times sine and I do 18 times 8, well, 18 times 8 is 144 degrees. I can't have a right triangle with 144 degrees. That seems a little off to me. That gives me an angle over here. 144 degrees is what I have traveled. Well, when I look at it on the picture, I realize, oh, well, if I did 144 degrees, the triangle that I used the other day was actually over here. Its reference triangle is going to be over here, and 144 degrees isn't inside that right triangle. I'm actually finding, well, let's see, this is 180 degrees. So this would actually be, oh, this would be 36. So that's actually this triangle here. So 36 degrees, that's actually finding point E. 144 plus 36 would equal 180. So actually after 8 seconds, I'm looking for point E's height. Well, we found point E's height yesterday. We found that point E was the same. It had that symmetry with point B. So it was exactly 44.7 feet above the ground. But I wonder if my equation would actually still work, if the little model that I made would still work. What does it even mean to take the sine of 144? So I'm going to try it out. What do I get when I do 25 times the sine of 144 degrees? Well, we still got 14.7. And that's what we're supposed to get. The sine function. Last year, we learned our trigonometric ratios. We learned sine, cosine, and tangent so that we could find missing angles and missing sides by using those ratios in a right triangle. But a right triangle, those angles only go up to 90 degrees. In order for sine to be a function, we needed to be able to plug in lots of numbers into sine. We needed to be able to go past 90 degrees. And so that's why trigonometric functions, even though they use the trig ratios, the functions themselves are traveling around a circle. When you travel around the circle, you can travel more than 90 degrees. For example, in this one, we traveled 144 degrees to get over to this angle. With the math, all you're doing for those angles is using that reference triangle here on the coordinate plane to help you find, well, what would that right triangle be that goes along with 144 degrees? And in fact, by doing this, it allows us to keep going around the circle. It allows us to say, well, I want to go 4 times around the circle. 4 times 360 degrees. We can get up into the thousands. We can get up into the tens of thousands. And all that means is that we're just traveling around the circle more than once. Wherever we stop as we're traveling around the circle, that angle that we stop at, we call that our terminal side. And the terminal side is what we use to draw our reference triangle. Wherever we stop on the circle gives us where we would draw that reference triangle so that we could figure out what is that height. And am I above the 30-degree mark or am I below the 30-degree mark? It even allows us with our functions to do negatives. If you're talking about positive and negative angles, in the function sense, What we're talking about is positive angles are always going counterclockwise, just like our Ferris wheel. So if we are traveling counterclockwise, we would give a positive angle. If we're giving a negative angle, it just means that we're traveling clockwise. And so the sine function, our trigonometric functions, are based on this circular idea so that our angles are not just limited to being between 0 and 90. Examine your calculations for finding the height of the rider during the first 5 seconds after passing position A. During this time, the angle of rotation of the rider is somewhere between 0 and 90 degrees. Write a general formula for finding the height of the rider during this time interval. So our formula ended up being 30 plus, and then we had to figure out what that little height was, and that's where we did the 25 sine, and then we did 18, that was our angular speed, times how many seconds had gone through. So our height on the ride was this for that first quadrant. And we talked about the different parts and where they came from. This 18 was our angular speed. How many degrees per second were we moving? And then this right here was our radius of our Ferris wheel. And this was our midline, that the spoke in the middle, that everything, the axle that everything was moving around was 30 feet above the ground. And so this was the building blocks that we had to use to figure out where we were on the Ferris wheel. But now if we're in the other quadrants, it kind of changes what we have to do. If you think about the Ferris wheel and its quadrants, remember this is quadrant 1, this is quadrant 2, this is quadrant 3, and this is quadrant 4. So what's going on? Anything up here we were adding, and anything down here we were subtracting. But that's also something that the trigonometric functions, the sine function, has been programmed to take into account. If your terminal angle ends with you being in quadrant 3 or 4, then the output of your sine function is actually going to be negative because it knows that it's supposed to be below the midline. If your terminal angle is an angle that ends up being in the first or second quadrant, then your sine turns out to be positive because it knows that it's supposed to be added to the midline. And so this function is actually going to be the exact same one that we use to find all of our different heights on the circle.